Hello, bonjour à tous. So it's my pleasure to start this 2 days. And so the keynote will be delivered by Professor Majed Chergui from EPFL Lausanne University, and as well working in Elettra and Fermi in Trieste. So, and your title is From Linear to Nonlinear X-ray. Did you keep this one?
Yes.
Okay, good.
For the introduction, I'm quite impressed by the audience and also by this auditorium. It feels like the United Nations, but much better. I haven't been back to Jussieu since, I don't remember. I took classes here when I was doing my master's degree. I don't dare say the year. It was 1978, I think. So it's quite impressive, the changes that one sees. Okay, so my talk is about X-rays, and I realized in somewhat late that I was the only one who was going to speak about X-rays. So I will do some introduction at the beginning, so that I try to convince you that X-rays are nice and that you can go from linear to nonlinear spectroscopy. And if you get this message, that's enough. The rest is not interesting. Okay, so there is this famous saying by Francis Crick, who was a co-discoverer of the double helix DNA structure. If you want to understand function, biological function, he meant, study structure. And so there are many techniques that give you static structures of biological objects, and that's already extremely powerful. But if you want to really understand biological function, you need to have it moving, and it's not going to move, as usual. Never mind. So this is an animation that shows the transfer of water through a channel in a cell membrane. What I want to say is that basically, I don't know why. Never mind. That if you want to understand things, the function of things or the reactions, you need to have them moving. And that's an old problem in science, which was first treated by this gentleman here in Paris, Etienne Jules Marais, who was a physiologist and an anatomist, so he was a scientist, who wanted to understand animal motion. And in order to describe animal motion, he wanted to take snapshots. And so he developed the shutter camera. And the shutter camera was called at that time le fusil photographique. And he took snapshots of all sorts of animals, including a very dangerous one here. And also, like cats, the famous, snapshots of cats falling poles up and landing on them. And if you take the cat, I like cats very much. If you take the size of a cat, let's say 30 centimeters, and you take the shutter speed that was in the millisecond range. Now you scale down the size of the cat to that of a molecule, so from 30 centimeters to 0.3 nanometers, then you will see that the millisecond scales down to picoseconds, sub-picoseconds. Later in his life, he also looked into fluid flow, did really beautiful films of the motion of flow. So, so it depends on of course, and we heard it already, it depends on the problem, scientific problem you have to treat, what time scale you're interested in. So again, animals, we're talking about milliseconds, but breathing takes microseconds to sub-microseconds, fluorescence, light, emission, thermal effects, nanoseconds. The isomerization of retinal in our eye, the vision, takes like 200 femtoseconds. Then if you go to lighter and lighter atoms, you have faster and faster timescales, like the vibration of water is about 10 femtoseconds. And you can go even further down into lifetimes of core transitions. And so in order to reach these timescales, there were different methods developed through history, from the stop flow to flash photolysis to relaxation methods, and that gave rise to a Nobel Prize to these three gentlemen in 1967. Then came the laser at the beginning of the 60s, and the laser quickly reached the femtosecond range, and that gave rise in 1999 to a second Nobel Prize in time-resolved studies of chemical reactions. So both of these are in chemistry, to Ahmed Zewail. And then, so these were all done, these studies were done mostly with optical domain spectroscopy, i.e. infrared, visible, ultraviolet. What we're interested in is going into the X-ray, and the light sources for the X-rays, especially pulse light sources, were synchrotron radiation, which could reach, which reaches still about 30 or 50 picosecond in pulse duration. You can go further down between 2000 and 2015. There was a laser slicing scheme that allowed extracting femtosecond pulses from synchrotrons, but soon came the free electron lasers, and they basically cover the entire range, and now they're going also into sub-femtosecond timescales. You also had lab-based sources, laser plasmas, that could generate femtosecond X-ray pulses. And more recently, we have broken down below the femtosecond, and that is the attosecond time domain, and as was already mentioned, a Nobel Prize was awarded in physics in 2023. So I don't know if there is going to be, after 20 years, another Nobel Prize in zeptophysics, maybe, I don't know. We'll see. Okay, so what can you do with X-rays in terms of structure? So you have one technique, which is X-ray diffraction, in which you have so if you want to do it in the time domain, you have a crystal, you excite the crystal with a short pulse, and you send the X-ray pulse to probe the motion that you have generated in this crystal as a function of time delay between the light pulse and the X-ray pulse. And so you could have, I don't know, melting, so the diffraction spots are going to blur away, and maybe recrystallization, so they will reappear maybe in another phase, or you can get coherent phonons, so you have the crystal breathing, and so you can get these diffraction spot oscillating, like was shown in this very first experiment using time-resolved femtosecond X-ray diffraction, where they saw the coherent phonons in a bismuth solid. But that's for solids, and in chemistry, this is not always what you want. So you want to go to solutions, and you can, oh gosh, why is this doing this? So you can go to solutions, and you have a liquid jet with a molecule you want to study, and you do the same thing as here. You pump with a laser, you probe with a time-delayed X-ray pulse, and now you detect the rings because you have a disordered system, and then you can retrieve the information about the solute, the solvent, and this is a nice example in the case of a cobalt complex, where again they saw nice coherent vibrations in the system. Now, this is one approach, but the title of my talk is about spectroscopy. So the other technique that is very much used in the X-ray domain is X-ray spectroscopies, and the simplest one is X-ray absorption, where you come from a core shell into the continuum, and you get these edge absorptions, so K shell, L shell, M edges, give rise to these nomenclature, and basically you get this edge every time you cross into the continuum. And with X-ray absorption, I'll go back to this in more detail, you can get the electronic structure of the atom, its oxidation state, and the local geometry. The other technique which we use a lot is X-ray emission. Once you have created a hole here, it's going to be refilled either by K alpha, K beta, or valence to core emissions. And this X-ray emission is a very nice fingerprint of the oxidation state, but also of the spin state of the system. And then you have the XPS, famous X-ray photoelectron spectroscopy, or UPS if you want, that gives you, and that's very important, the absolute binding energies, because you reference with respect to the ionization continuum. And you get also very important information about the chemical bond by looking at different atoms, identical but inequivalent atoms within molecules. So core level spectroscopies are very rich. There is a whole zoo of acronyms, many, many more. Some of them you don't want to say in the presence of children. We have, I will focus now mostly on X-ray absorption, just to make the point about what you can get as information out of it. So you know from undergraduate physics textbooks this type of spectra. This is the X-ray absorption spectrum, where you see the K shell absorption and the L shell absorption. I want to point that Charles Barkla obtained the Nobel Prize for discovering X-ray absorption in 1911. That was 2 years before Lauer and the Braggs, I think, who discovered X-ray diffraction. So he had no dispersive elements when he did his discovery. He used metal filters, and he found that there were edges. And when he found two edges, the first two edges that he found, he took the first two letters of his name, BA. And then he thought, well, maybe the people will discover new edges. So if you start from B, you go to A, then there is nothing afterwards. So he switched to KL. That was quite nice of him, because then people discovered the M edges and the N edges and the O edges. So anyway, if you zoom into one of these edges, you have a lot of fine structure. These are under the edge, or if you want the ionization threshold, bound-bound transition, atomic transitions. Then you go into the continuum and you get these modulations, which are due to the fact that you generate a photoelectron. And this photoelectron here, this is the isolated atom. And once you have a neighbor, this photoelectron will backscatter onto the neighboring atoms and give rise to modulations of the absorption coefficient, which are classified as XANEs and XFs. And basically, I mean, in a nutshell, you have this situation where the photoelectron, this is a classical picture, is backscattered, and you have interference between the outgoing and the backscattered wave, just like you have on a still water in a pond. So the XANEs has the advantage that it has a high, it's in a region where you have a high, a high scattering cross-section, so you get multiple scattering. And so with XANEs, you can get the local structure, the three-dimensional structure, whereas the XFs region is only one single scattering event. And so you get mostly bond distances and coordination numbers. So why is X-ray spectroscopy so interesting? You can apply it to any medium. It's element specific, so you tune to specific absorption edges of atoms. You can detect optically silent species, something that we very much exploited. And you get very much information about electronic structure, which you don't in X-ray diffraction. You don't get that much information about the electronic structure, in particular the density of unoccupied or occupied states, the valence, the nature of the valence orbitals. When you come from a core to the valence orbitals, you are interrogating the valence orbitals, and these are the guys that are doing the chemical bond. So that's very important. Any changes in the molecule or the system is going to be reflected in your spectrum. Degrees of oxidation, local symmetry, spin state, and in a way, if you want to call it a drawback, you only get bond distances and angles of the local geometries, not the global structure like you get in scattering methods. But we didn't care because we were interested in ultrafast phenomena, and the short time scales correspond to short length scales. So that's fine as far as we are concerned. So over the years, that started about 25 years ago, we looked at different phenomena like intramolecular charge transfer in metal complexes of interest for solar energy conversion. We looked at spin crossover dynamics. This is interesting for magnetism. So these are molecules, metal mostly with iron or cobalt that undergoes, delta S equals 2 spin changes under the effect of light, temperature, or pressure. We studied them under the effect of light here. Bond formation in bimetallic complexes, plasmons in metallic nanoparticles, solvation dynamics, how the solvation shell changes after you excite a solute. Protein dynamics, I'm going to go into more details now. Transition metal oxides, we looked very much into both sensitized and non-sensitized transition metal oxides, different type, titanium dioxide, nickel oxide, cobalt oxide, and also more recently, perovskites. I'm not going into the details here. What I want to say is we did the first phase of the work with synchrotron radiation, and then later on, around 2010, the free electron lasers came into operation. The first one was in Stanford, and there was one in Japan, and later on, others came into operation. This was a hard X-ray machine. As you can see, the length of the machine is in kilometers. And one of the first soft X-ray machines was in Trieste at the Elettra Center. And then in Switzerland and in Germany, 2 more machines came into operation. Basically, they are laser-like. They are not actual lasers, except for the Elettra free electron laser, because it's seeded by an optical laser. Anyway, the big advantage of these machines is that compared to synchrotrons, where you reach the 50 to 100 picosecond pulse duration with typically 10 to the power 6 photon per pulse, here you go into the sub-100 femtosecond, and you have 6 orders of magnitude more in flux in the hard X-ray regime, and 10 orders of magnitude compared to the slicing, which was a technique used to extract femtosecond pulses from a synchrotron. So it's a big, big advantage, and that also justifies a drive towards nonlinear X-ray optics. So after this long introduction, I'm going to give you some examples. One is about linear pump probe X-ray spectroscopy of heme proteins. And the second is about nonlinear chemistry techniques. And then I will tell you something about more recent X-ray studies that we started in my group on chirality. So heme proteins are very important because we have them in our blood. And this was a work that Linus Pauling did publish in 1936, and he said that Michael Faraday had investigated dried blood and had noted that he should try recent fluid blood. If he had determined the magnetic susceptibilities of arterial and venous blood, he would have found them to differ by a large amount. And that's very important because this is where you have a switch in the structure of the heme. So let's introduce the heme first. So this is hemoglobin, and it's composed, it's a tetramer of 4 myoglobin-like proteins. And myoglobin, the bioactive center, is this porphyrin. So you see it here with the iron atom and the ligands, typically oxygen, but you have all sorts of ligands that bind to this iron, NO, CO, H2S, CN, what have you. And what happens is when we breathe, we take in oxygen. The porphyrin goes, so typically it is planar when it has the oxygen bound to it. When you release the oxygen, it goes domed. So this is arterial blood, this is venous blood. And what happens is really that this is what I call the transition state of the respiratory function. At the very beginning, what happens is you go from a low spin when you have a ligand bound to the iron to a high spin. And when you go to the high spin, you populate antibonding orbitals, and the iron N bonds elongate, and therefore it turns the porphyrin into a dome. Now, why has this to do with the respiration? That this iron pushes on this histidine. This histidine is bound to this helix. This helix then sends a message to the other units, monomers, that oxygen has been uptaken by one of the monomers. Now, a phenomenon happens called allostery in hemoglobin, that once one monomer has taken up an oxygen, the affinity of the others to take up oxygen increases. So this is a cooperative reaction in biology, very fascinating, which is not fully understood, but the hint that was given by Max Perutz, one of the guys who determined the structure of myoglobin, is that it should be some mechanical signaling via this F helix that is on the other neighbors. But anyway, let's go back to the very initial event, which is of interest to us. And in fact, hemoglobin and myoglobin should be really very important to any ultrafast spectroscopist, because, not because, I mean, they should be close to their heart, not because it's only, blood, they are the main constituents of blood, but because the very first femtosecond studies ever done were done by, on hemoglobin and myoglobin. So the first paper appeared in 1976. That was with a 500 femtosecond pulse by Chuck Schenk, the guy who developed the femtosecond laser. They published this paper, and then there was nothing published until here in France, Jean-Louis Martin picked up the problem again and pioneered the femtosecond studies of heme proteins using femtosecond lasers. It was quite an achievement if you think about it. And it was also the very first system to be studied by time-resolved X-ray absorption spectroscopy. So that was done at Cornell, at Chess at that time, at the synchrotron, with millisecond resolution. Never mind. I mean, they photolyzed myoglobin with a CO ligand, and they looked at the change in the edge, which is due to a change from planar to domed, as I mentioned before. So despite this long history of studies, starting from the early 80s, there were still questions. How fast is doming when you release a ligand by a pulse? Is a process driven by electronic effects, or is it a thermal effect? And there's been a debate about that for ages. And I dare say that we came in with the X-ray because we were the first ones to look specifically at what the atom does. And I'm not going to go into now showing you the results and the spectra and the transients. I just want to summarize what we found. We studied different type of heme proteins. This is myoglobin with an NO ligand. All these are ferrous heme proteins. We looked at cytochrome C. Cytochrome C is very important for electron transfer in the body. And again, a ferrous porphyrin. And you see that there is some pattern which is very similar in the cascade, and that this cascade proceeds via spin states. So you excite the pi star of the porphyrin, and you end up in an intermediate spin of the metal, and then a higher spin of the metal, and then you relax back. Now, this step of the relaxation is very different from porphyrin from heme to heme, because it involves some chemistry. In this case, you have an NO ligand. In this case, you have a methionine ligand. They don't recombine the same way, and that is mainly the last step. But the important ones are these steps. And if you look at the literature, optical domain studies also hinted to similar values. This is with a CO ligand. This was an X-ray work, sorry, also by the group of Levantino et al. And this was an optical work. And again, you see a very similar pattern in the time scales of the initial cascades. And that reminded us of a class of system we studied a lot, which are the spin crossover iron 2 systems. We and others, and we found that the spin switch from S equals 1, S equals 1/2 to S equals 2 is extremely fast, and typically on the time scales of a few hundreds of femtoseconds. So the photophysics of heme proteins is very much identical to that of spin crossover states. So, whenever you feel dizzy and you go into a high spin state, this is all governed by spins. It's not so much. There are not so much thermal effects in heme proteins. So with this, I wanted to give you an example of what X-ray spectroscopy can do. You have to combine of course, we used optical domain spectroscopy, transient absorption, and fluorescence subconversion, which we combine with our X-ray absorption and X-ray emission work. So you get all these fingerprints of the spin states in a very clean way. Now, I want to switch to nonlinear spectroscopy. One would ask first, why do you want to go to the extreme ultraviolet or the X-ray domain? These domains are those of the core transitions. So, in fact, again, I want to stress that the advent of free electron laser is putting us in the same situation as the advent of optical lasers in the 60s, where thanks to the laser, we saw the birth of nonlinear optics and spectroscopy, and here we're exactly in the same situation. So one first obvious advantage is that you get element selectivity. So now you can look in a nonlinear process at atoms, specific atoms. You are structure sensitive. You can access large momentum transfers that I'll come back to in a second. And you have to bear in mind that when you go to short wavelengths, concepts like inversion symmetry have to be adapted to short distances. So sometimes crystals that don't have global inversion symmetry or do have global inversion symmetry lack it when you go at the level of reticular planes in a crystal. And you can probe, depending on the type of radiation you use, bulk versus surface effects. So the history of nonlinear core level spectroscopy starts quite a while ago, well before the advent of free electron lasers. There was a spectacular experiment done, the parametric down conversion in the early 1980s, which is a parametric down conversion has some variance resemblance with difference frequency generation, where they they use an X-ray tube on the diamond crystal, and they got emission of another X-ray photon and an XUV photon, when the sum of the two corresponded to the incident radiation. I think it was copper K alpha or something like that. Really very impressive work. And then 10 years later, this was repeated at the synchrotron. But we can say that now, over the past 10 to 15 years, all the major nonlinear tools that we know in the optical domain have been demonstrated in the X-ray domain. So stimulated X-ray emission, stimulated X-ray Raman, two-photon absorption, Rabi cycling, this is more recent, and second harmonic generation. So I like second harmonic generation in particular because we are working on it. So in second harmonic generation, as you know, you come in with an incident beam, and you detect the double frequency after passing through the sample. This is a Chi-2 technique. The other Chi-2 technique is sum or difference frequency generation, and there was a spectacular experiment done published in 2012, where they had a diamond crystal, an X-ray beam at 8 kilovolt, and an optical beam at 1.5 kilovolt, and they managed to see the sum of the two in analyzing the emitted light, and they matched in order to have a good phase matching, they also matched their vectors with the inverse of the lattice, with a lattice wave vector. And that was quite impressive and was not repeated until this year on silicon crystals, which are quite similar in some of their properties to diamond. So this is very nice because Chi-2 techniques allow you to really now look into surface or interface chemistry with atomic selectivity. You can look at catalysis, and you can use it also for chirality, which is one of the avenues we're pursuing. The other nonlinear techniques are four-wave mixing techniques, which are Chi-3 techniques. And one of the most popular one is transient grating spectroscopy, which I'm going to tell you about, and was pioneered at Elettra by the team of Claudio Masciovecchio. And recently we published a review of all these techniques at the XFEL's Nature Physics reviews. So transient grating spectroscopy is one of the first nonlinear optical techniques to be developed. Basically, you have two identical wavelengths beams that come under different directions, so different wave vectors, and you interfere them on the sample. So you're going to form an interference pattern of excited, unexcited, excited, unexcited regions. And then in order to follow the evolution of this, so that could be an excitation, electronic excitation grating, a thermal grating, a magnetic grating, whatever, you come with a third beam and you diffract onto this grating. And as the grating fades away, you can follow its evolution in time. And you detect this probe pulse in a different geometry, so this is a background-free technique. So as I said, you have different types of gratings. Now, if you use optical light, so the grating period is given by the wavelengths of light and the crossing angle. If you use visible light, typically you get gratings of 1.4 to, typically 1 micron. So transient grating spectroscopy is very much used to look at the transport phenomena in solids and liquids and even gases, and it's extremely well established. But if you go now to shorter wavelengths, you see that in the soft X-ray range, typically 12.4 nanometers, you can make grating steps of tens to hundreds of nanometers. So now you are starting to enter really regions of transport phenomena at very short distance scales, so nano to meso. And if you could do it also in the hard X-ray, and I will show you that we did it, then you go into the nanometer scale. Now this is very important because people who are looking at transport have no clue what happens at very short distances, especially when phenomena change from ballistic to diffusive transport. And I always think that, maybe I'm a bit idealistic, that transient grating spectroscopy could be an application for electron lasers, because people who are working on the nano and micro in nano and micro electronics have no idea how heat is managed in these nanostructures, or excess charge, all these things. So this could be a way of looking into it. So these are the advantages of going to shorter wavelengths. And as I said, you have high momentum transfer. That is, you can look at high frequency responses, high temporal resolution, element selectivity. And by the way, transient grating spectroscopy was the stepping stone towards multidimensional optical spectroscopy when it was in the optical domain. And people are hoping that it will be the case for core level spectroscopies. That is, when you use two different wavelengths instead of identical wavelengths, so that you can tune, so you can do 2D spectroscopy. Anyway, okay, enough for the publicity. The first experiment that was done demonstrated transient grating spectroscopy in the extreme UV was done, as I said, at Fermi, at the Elettra Center, and they used two photons at 45 eV, which they cross onto the sample, and they probed them with an optical pulse, and they got these nice responses with electronic response and optical phonons and acoustic phonons and so on. So this was really a proof of principle. But now, when you create a grating which is in the tens of nanometer scale, and you come and probe it with 400 nanometers, the spatial information that you gained from making this grating with a short wavelength light is lost. You see interesting things, but you don't have the spatial information. So the next step in this group was to go to an all EUV transient grating experiment in which the optical pulse is replaced by an EUV pulse. And in order to do this, they used their extreme UV optics, where you have the beam coming from the free electron laser. You split it in two. You generate the probe beam here, and the rest of the beam here, you split it again in two, and you generate the two pump beams. So you cross these two identical beams. All three beams are identical in reality, but one is time delayed, the green one, with respect to the other two. So you can probe the system as a function of time after impinging the grating on it. And compared to the optical response in this experiment, they got a different response with the EUV probing. This response at short time is pure electronic, whereas here they only get the structural response. That's because when you use an optical probe, your index of refraction is strongly determined by the charges you have in the valence and the conduction band, and it's much more sensitive in the optical domain than in the X-ray domain or the extreme UV domain. But anyway, these are beautiful proof of principles. What happens when you go to the hard X-ray? Now, the hard X-ray, you don't have optics like that. So you have to really scratch your head. So Chris Vettina, with whom I collaborate since years, had the beautiful idea of using the Talbot effect. The Talbot effect was developed in the 19th century. It's basically you have a grating and you have a plane wave coming onto it, and then you have different orders of diffraction. And these different orders of diffraction will overlap each other's at regular distances called the Talbot distances. And the Talbot distance is determined by the spacing of the grating and the angles, and the wavelengths. Well, the angles too. And so you can place your sample at one of these Talbot planes, and you can reproduce the mask onto the sample. And so we did this first to do a permanent mask, and we found that indeed you can reproduce a step of the grating on the sample, and then you can then use this to do transient grating spectroscopy, like here. So you come with incident beam, you create the grating, and you probe it with an optical beam. So the first demonstration of this process was published 4 years ago, and you see the response of the transient grating. So this is, at this stage, we did this experiment, by the way, at 7 kV, probed at 400 nanometers. We didn't bother about going into very, very tight gratings. We just wanted to see that we created a grating with these high energy photons, and we could probe it, and you see coherent phonons. This is a bismuth germanate compound. But then, again, as I said before, if you do it with an optical probe, you've lost the spatial information. So the next step was to do an all hard X-ray transient grating spectroscopy experiment, where we took a silicon sample and we created so we had two. This was done at the Sakura free electron laser in Japan, which could produce two-color X-ray pulses at 5 and 7 kV, 5 femtosecond pulses, pulse widths, and the time delay could be tuned between the two. And what we did here is we create a Talbot carpet, send the probe beam through it, we detect the transient grating, but we had the other advantage of being able to detect diffraction peaks sideways. So we had two detection schemes, one of the transient grating, but one also of the actual grating of the crystal. And what we found is very noisy, but it's very interesting. You find this response with a sharp peak at the beginning and then oscillations. And if you look carefully, you see that the peak appears with some delay, typically 15 femtoseconds, and these are the two detection channels, transient grating or diffraction. And this oscillation is typical of the optical phonon that you have in silicon. It's been observed by optical methods and other methods. But the interesting thing is the first peak of this oscillation appears after 15 femtoseconds. And that's a time scale for electron-electron scattering and the transfer of energy from electrons to phonons. That's never been measured in real time. And this is one of the first manifestations. And we believe that these techniques will be extremely useful to understand how these, the hot photo and Auger electron that you generate by the first X-ray pulse are going to transfer their energy to the phonons. Okay, so that was for transient grating spectroscopy. Can we do it in the liquid phase? Yeah, because the liquid phase is important for chemistry and biology. So we did an experiment. I'm going to skip some of the slides because I'm running out of time, where we took this ferrioxalate molecule that undergoes a photochemical reaction. When you excite it, you have a bond breaking of these ligands and a recombination, and we wanted to follow the reaction. I'm not going to go into the details. What I want to show here is that we see very clearly a transient grating signal with a certain temporal evolution. And if you scan across the iron edge of the solute, you see that you have an increase. Basically, the intensity maps out the absorption edge of the iron. And we're still analyzing these data. They're not completely analyzed. This is work in progress. But I just wanted to stress the fact that we can do this experiment in the liquid phase. This is quite important for future experiments. Of course, the pump beam in all these transient grating experiments is a core level transition. So, you know, if you are bothered about that, that's a different issue. But if your goal is to look at transport processes, once you have generated whatever, charges or heat, then this is really ideal, and especially for going into small grating steps. Okay, now my last few minutes, I will tell you about chirality. So after I retired from EPFL, I moved to my activities to Elettra in Trieste in Italy after earning a new ERC grant called Chirax. So I don't think I need to tell you about chirality here. I mean, it's the fact that you have objects that are mirror images of each other, but they cannot be superimposed on top of each other. And that plays a very important role in pharmacology, in drug design, and in medicine. And the way to detect chirality is still, to this day, at least, and let me stress, for molecules in solution, which is very important for biology and biochemistry and chemistry. The way we detect them is by doing circular dichroism spectroscopy, where you have left and right-handed circularly polarized light that are absorbed by the sample, and you look at their difference. And this difference is tiny because in the light-matter interaction, I mean, we're in the LUMA PEPR, so I have to talk about the Hamiltonian of light-matter interaction. You have the term due to the electric dipole, and here you have the term due to the magnetic dipole, and then higher terms due to the electric quadrupole. And these terms are really tiny, and that's why the response is so small. So our idea was to try to enhance the sensitivity, again, for molecules in solution. So we thought, okay, let's extend CD spectroscopy to the X-ray range. For one thing, these higher order terms, magnetic and quadrupole, scale as A over lambda. And so if lambda goes down, then you should get an enhancement corresponding to the wavelengths of the signal. But that's the tourist brochure. The reality is very different because the transition dipole moments for valence and core transitions are very different. So the signals that you get in the X-ray are not so intense or so anticipated to be so intense. But nevertheless, you have element specificity. And the fact that another element specificity is that the dichroic response depends on the chemical environment for a given atom. So if you have identical but inequivalent atoms in a molecule, which traditionally you distinguish by the chemical shift, but sometimes it's not always easy to separate, you know, in energy, the different chemical shifts, then here you have an additional parameter to play with, which allows you to look at the dichroic response of these identical but inequivalent atoms. Again, I insist, we are talking about solution. In isotropic media, the electric dipole, electric quadrupole contribution vanishes. Now, can I show you this? No. Okay, let's jump. So to illustrate the fact that different identical but inequivalent atoms have different responses, there are several simulations that were done over the years. There are actually more simulations on the subject than there are experiments in the X-ray domain. And here you see noradrenaline, for example. You see here the absorption spectrum at the carbon edge where you see highly congested regions. And if you now run a CD spectrum and X-ray circular dichroism, you can very easily disentangle what is what under these blobby features. There was a calculation even done for C84 where they could predict disentangling the X-ray absorption spectrum of these identical but inequivalent atoms. So we looked into the literature, and until recently there were only very, very few studies, and you can count them on the fingers of one hand, that were done on powders of amino acid residues, because you have to tune into the oxygen, nitrogen, or carbon K edges. You have to work in the soft X-ray, and therefore you have to work in the vacuum, and that's why people mostly used films or powders of these compounds. And these are the few studies that were done. They are not always so convincing, because if you have a solid sample, then you have radiation damage, and it's very difficult to get the mirror images typical of circular dichroism spectra. Only one study looked at XCD at the carbon edge, and that was for a disordered system, for a dilute system, that was gas phase methyloxyrane in 2004, again at Elettra. And they got these XCD spectra. And we looked more recently in the hard X-ray, but that's not circular dichroism. We did helical dichroism of enantiomeric pure powders of an iron spin crossover compound. And we got the mirror images for different topological charges. I mentioned this because someone spoke about, in the introduction, about the fact of using light to drive chirality. So this is the first, to my knowledge, the first study of X-ray helical dichroism on molecules so far. But in the liquid phase, there was nothing. So in 2015, these flat liquid jets started appearing, where you can now do X-ray absorption spectroscopy with these thin jets. Typically, we are talking about micron-thick jets that you inject into vacuum, and we decided to use them to do X-ray circular dichroism spectroscopy, and we did about 3 experiments within 1 year. The last one was done at Pléiade in Soleil, but I'm showing only one result, the one that we have well analyzed so far, and this is alanine, I think. Yes, it's alanine. No, cysteine, yes. L-cysteine, so the left-handed cysteine. These are simulations, absorption spectrum and CD spectrum, and these are the absorption spectra and CD spectra that we got at the beam time at Bessy. Last May, we had beam time at Soleil. We have very promising results, but the analysis is not finalized, so I'm not going to show them. Now, I stressed a lot about X-ray work, but in reality, we have always, whenever it was necessary, we've combined a lot of techniques, and that brings me back to some philosophy. The legend of the 6 blind men and the elephant, and each one touches a part of the elephant and says, okay, this is a rope. The other one says this is a pillar, this is a pipe, this is a wall. They all are right in a way, but they don't get the global picture. So you really have to combine all these techniques, which we did in my lab, to account for the totality of truth, if possible. And with this, I'd like to thank my collaborators at the different. So here, this is my team at Elettra, and all the collaborators, different synchrotrons and free electron lasers with whom we collaborated, and theoreticians and many other people. And I thank you for your attention.
Thank you, Majed. So now it's a time for questions. Is there any? Yes, Elisabeth?
Hello, thanks for the beautiful talk. I'd like to ask you about the CD in solution. So you quite rightly mentioned that electric dipole transitions will disappear in isotropic media. But if I don't really quite understand the mechanism, if you suggest that it's electric dipole, magnetic dipole, but we're looking at core continuum transitions. So magnetic dipole transitions should be forbidden by the selection rules. So can you explain what part I'm not understanding?
So I'm not sure I got your question, you say?
So you presented these results on circular dichroism in solution and said that these are arising from electric dipole, magnetic dipole interference. But if we're looking in the X-ray range, as opposed to the UV visible range, we're looking at core continuum. So I guess you're looking at 1s to continuum transitions, which would be forbidden by the magnetic dipole, which can only occur within the same quantum number.
Yes. So that's interesting. Thanks for the question. So when in light atoms, the energy gaps between these different orbitals, different levels, core levels, is small, and therefore you get configuration interaction and core hole relaxation that also play a role. So you do get mixing between the different orbitals, and you borrow, therefore, some intensity. But we're doing experiments. We've done some experiment at the sulfur L edge. So you go from P to that seems to work also quite well. So yeah, good point.
Any other questions? Yeah.
Yes, Majed, many thanks for this really nice talk about the last part on the CD of cysteine in solution. I mean, just from this simple spectrum that you showed, what do you learn about the molecule, about the structure, or its potential dynamics? I mean, did you play with pHs? Did you look at various core levels? I mean, what do you learn from just this picture? I mean,
okay, very good.
Beyond the fact that this is a tour de force, I know it's super difficult, but
I can stop you there. We don't learn anything. I mean, this is no. X-ray CD of liquid solution has never been done, so we are struggling, because it's far from easy in demonstrating it. First, I can explain the reasons. I mean, when you scan a CD spectrum, you scan left polarization, then you scan right polarization. When you do this, and the signals are very weak. Already in the optical domain, it's not a trivial technique. If you're doing this at the synchrotron, you have to scan first, switch the polarization, scan again. During the scan, lots of things can happen. You have the decay of the photon flux, you have instabilities in the liquid jet, then you have a minute to switch the polarization, do another scan. All sorts of things happen. And we are really still struggling with this. So we're quite proud of this result, even though we are not yet at, learning what the molecule does and look at these effects, because we're not yet completely, rock solid about the data acquisition strategy. You need to have a lot of references. This is a dilute system. In reality, the reference is not the I0 beam, but it's the I0 through the pure jet, and it's impossible to record at the same time a solution and the pure solvent. So you see all sorts of artifacts come into play, and you have to be really, really careful about reproducibility. So we're at this stage. Yeah. And I didn't have time to discuss it, but in fact, we want to go on in this line, but we are now working on another line, which is to use Chi2 techniques. So combine optical and X-ray pulses and do some more difference frequency generation, because in this case we anticipate background-free, better signal and direct information about the chiral solution. So it was already demonstrated in the 60s that Chi2 techniques can be applied to liquid solutions provided it's a chiral solution. And you get a response from the bulk, not from the interface only. Yeah? Okay.
Thanks.
There is another question by Anne.
Thank you, Majed, for sharing these beautiful results. I have a question also on core shell CD, because for electronic CD, when you have similar orbitals, they can couple in some sort of exciton coupling with opposite CD signals. So I was wondering whether if you take similar or identical carbon atoms, do their core shell CD give opposite signals too, or for example in the helicene molecule?
Yes, I mean according to theory, yeah? Because we haven't had the chance or the privilege of demonstrating this yet. But according to theory, I mean you can see here, for example, under this feature or under this feature, you have differential responses. I don't know if this answers your question.
We can discuss later. Thank you.
Any other one? Okay, I have one. How long did it take to record the? Roughly.
This X-ray CD.
Yeah.
After 2 weeks of measurements.
Yeah. Okay.
No, but I mean we recorded. No, it takes recording the spectrum takes. Let's say 5 minutes, and then 5 minutes with the other polarization. Okay, but then you get lots of data and you have to analyze it. We took 2 weeks of, it wasn't difficult to get the absorption, by the way, sorry, I forgot to say this is nitrogen KH. It wasn't difficult to get the spectra, but to see what makes sense took some time.
And I have another question about the X-ray transient grating and X-ray diffraction. Would it be interesting to, instead of to use an optical light to probe the grating, to go, I know that it's more demanding in terms of photons and stability, but to go to the X-ray probe, meaning that you create some change of the indices due to all the electronic excitation, and then probe to another age?
Yes, it's been done, by the way. So you mean do the grating with an optical pulse and probe it with an X-ray?
No, everything X-ray, but not the same KH, or not the same
yes,
LH.
but in fact this was done here. It was not at an edge, by the way. Sorry, we were not tuned to a specific edge, but we used two colors. Here we use two colors. Yeah. So we did try also at the European XFEL to use two colors tuned to different edges, but for a reason that have nothing to do with the edges, the experiment didn't work.
Is there last questions? No? Okay.
There was one here.
Regarding your point about helical dichroism, could you maybe tell a little bit more about what helical dichroism enables compared to more conventional circular dichroism?
Yes. Well, I mean, you come with different orbital angular momenta. I didn't describe the experiment. Here. So we did this at the synchrotron at the Swiss light source, and we had these spiral zone plates that allowed us to choose the topological phase of the light. Now, the whole difficulty of this experiment is you are using a ptychography beamline, because you need to make sure that you have the right phase, So, and these ptychography beamlines are not always adapted for X-ray spectroscopy. That means scanning spectra. So that was quite okay. So anyway, you see that if you have orbital or angular momentum L equals plus or minus 1, L equals plus or minus 3, you see this mirror images and so on. Now, the big advantage of helical versus circular dichroism is that you can choose. You see circular dichroism, you have S plus or minus 1 and 1/2. Here you go from 0, plus or minus 1, plus or minus 3. So you can really adapt. We don't, I'll be honest with you, we don't fully understand these spectra. Jérémy is still working on the theory. But I think there is a wealth of information about higher order effects in the system that one could pull out. I mean, this is really the beginning, in my opinion, so, yeah.
Okay, we will thank again Majed.